Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about variable refrigerant flow, or sometimes you will also hear the word volume. So we are talking about VRF. So let's dive deep into it. So what exactly is the problem that we need VRF? Well, reality is all times our demands are mixed and dynamic, meaning one thing will not be sufficient to suit every scenario. Especially at medium scale dwelling, meaning when you're talking about a single household and all it is like, hey, let's make sure the bedroom is cool. That's one AC's job. You done, you good. Like if you are talking about like, two or three rooms, that will still work fine enough. Like have individual air condition or have a centralized system, that will still work. However, the moment scale starts to go from like, small to medium, yeah, like small hotels, hospitals, large housing systems, yeah, then things can become messy. How messy? Well, here's the deal. You may want heating and cooling at the same time. Meaning, some people are like, let's just say the scenario where somebody is like, bro, it's freezing out there, and the other scenario is like, bro, we need to like cool down. So all those things create a scenario where one dwelling, if you have multiple households, as in like multiple flats, is like, hey, somebody who's working in the gym in the winter is like, I need like cooling, and somebody is like, dude, I need heating. So, and again, if you have a hybrid system, basically you have you want to dump that heat into heating water. Again, hot water is needed in summer also, like for your dryers, for your basically dishwasher, for your washing machine. You need that. So that's a very what you call complicated problem. It's like you have the units, as in like you have the heat exchanger, you have the refrigerant, you have the stuff, but the demand is confusing. So you may want to cool some place and heat others. So that creates a scenario. And load is variable, meaning you can't perfectly balance it out. Even though we will love to do so, that will consume the least amount of energy. Like, hey, I have this waste heat and I need this place to be heated. Take the waste heat, dump it into there. Perfect. Oh, I need cooling. Take the heat from the air, dump it into where I need that heating. Perfectly balanced. But we don't have Thanos in real life. So that creates a scenario where load is variable. So we need something that is flexible. While air condition is good, it got us so far. We need something bit more wiggle room. So what does normal air condition mean in this scenario? Well, it's a simple refrigerant loop that has two heat exchanger. Let that be very clear. You can say they are evaporator or condenser, but those are task. What they are is heat exchanger, and that task can be flipped. Especially like for right now, my air condition is a Blue Star unit, old unit. It has heat pump, meaning in winter I'm using it as a heater. It's dumping heat. Now the evaporator and condenser now switched places, meaning the indoor unit is the condenser, outdoor unit is the evaporator. That's why technical term is heat exchanger, not condenser or evaporator, especially if you're talking about heat pump kind of system. So you have two heat exchanger, you have one compressor and expansion control valve. Now expansion control valve, generally you could find some dumb ones, especially at low cost units, and we can add things to it. Like that's the base system, meaning you have a compressor turns hot, takes the gas that is like low pressure, you pump energy into it, to it, you increase it into a very high pressure, then you send into heat exchanger blows ambient air to it, it dumps the energy. So this output temperature has to be higher than your ambient. So let's say ambient is 50 degrees Celsius, the compressor output has to be 70 or like 55 at least. Then it will blow the air up through it, and that will allow it to cool down the liquid, basically go from phase change, as in gas becomes liquid. That liquid now has dumped its energy. That liquid goes into your capillary based expansion valve. That expansion valve limits is like, bro, don't flood it, like just relax, chill, and after that it goes into liquid state into your evaporator side. That evaporator boils that puppy. Boiling simply means eating heat away. So once you heat, heat this evaporator, aka it cools down your room, it goes from liquid to gas. The refrigerant boiled away. Then it's a low pressure gas that goes into your compressor repeats the cycle. So that's how everything works on a base dumb system. We had this from 1950. It's strong, it's robust, it works. You can have a lot of refrigerant options, and it's a very decent system. However, this is on and off system, meaning you can either start it or you can turn it off. There is no throttle, there is no valve, there is nothing to it. So this is a very base load system. But again, we have made progress, so we add things to it, few things to it that makes it far more adaptable. Because in this scenario, you have what we call temperature oscillation, meaning it's temperature system. Let's say you set it to 25 degrees Celsius. It work starts, right? Let's just say it's hot, 35 degrees Celsius indoor. It will wait for it to, compressor will keep running until it drops to 25. Cool, here's deal. It will not stop there. Compressor will not turn off at 25. Compressor will wait for it to grow to, let's say, 23. It will go below. Then it will wait for the temperature to rise above 25. Once it rises above 25, it will keep cooling it down until it goes. So there is an oscillation there. Why is that? It does not have any throttle. It's just like on or off. So that creates a lot of oscillation. More than good enough, especially because your room air acts like a low pass filter. It's like a filter scenario. It has so much mass, it's buffering it. But we realized that we could do better, and we added variable frequency drive, aka some ability for this RPM to be controlled, because compressor systems generally, not all, but most compressors have this benefit where if you reduce the RPM, you reduce the pressure. So how things are condensing, that changes. Basically, how much energy is consuming, it changes. So adding variable frequency drive, VFD based systems, VFD is in older systems. Nowadays, many ACs literally have BLDC motor. So VFD would be in air alternate current motors. BLDC will have its own motor driver. So that allows you to throttle the compressor. That gives you one variable. Second, this expansion valve is like a fixed throttle position. It's like, that's it, the end. So they always optimize it for one scenario, but that's a very wasteful. So how do you tune that part? Well, you have electronic control expansion valve. So that valve controls the flow. So you can have a scenario in modern air condition, and I'm talking like simple air condition, where your AC can go above 100% for short duration. Basically, let's just say you turn on the AC, it detects that room is very hot. It's like, okay, I'm gonna go YOLO. So it can run at 100% power or 125% power for few minutes, and it will start to drop down temperature very quickly, and then it will start to fine tune. Now, because it has two variables for fine tuning, aka the expansion valve and the compressor, it can really tone down the cooling capacity. Instead of going on and off, it's like, okay, I'm going to work at full power, let's say 2 kilowatt, base load power of 1.5 kilowatt, it runs, and then it's like, okay, I've reached the temperature, now reduce the power consumption. Rather than turning off, reduce the power consumption. It can go down as low as 400. Of course, it will turn off if, like, especially at night, if once people are sleeping, our body is not generating as much heat, so it has to have the ability to turn off. But, like, instead of oscillation, you get a very smooth maintenance. So that's how we made normal AC more optimum. Then somebody's like, hey, why, like, remove parts of AC and then rotate it around for winter? What if you added a four-way reversing valve, this puppy? Now, this four-way reversing valve is very convoluted, and the primary penalty with this puppy is it will reduce your air conditioning efficiency. For example, when I bought this heat pump unit, Blue Star unit, at the time of purchase, I did my best. I did search high and low, and I could not find a single goddamn air conditioner that had this four-way valve and had 5-star energy rating. They all had 4, and I was confused. Then I realized this system works on compressor gas power, meaning it's literally leaching power away. So of course the rating would be a bit lower. So you have a solenoid valve, basically that switch, a small on-off switch that basically sends the high compressed gas sends into right position. So it will like ka-chonk it here or ka-chonk it here. So this is how you can flip, because it's a 4 positions, so you can flip it. So this way you can have the condenser be outside or evaporator be outside without physically moving anything. You're just moving this valve, so to say. And this valve alone will not work, because again, this expansion valve is designed in one way. So you have to have another check valve and then another expansion valve in other direction, so it works in both directions. So you do have to add 3 things. So one-way valve and basically double one-way valves and double expansion valve, and then one this what we call 4-valve system. It does add parts to it, but all of these are rather simple devices, nothing fancy, nothing too complicated, and it does work. Like, heck, right now it's working. So it's a very elegant scenario. Basically, now we can have a scenario where AC is working as a heater, AC working as a cooler, and we also have throttle control, aka it's not just like full on or full off. So this is how far we have gotten. Now, we are a variable refrigerant flow or volume. Volume you can't say simply because that's a Daikin's trademark, and other companies cannot say. Now, be mindful, patents expire, trademark does not. So patent has expired, I'm reasonably sure. So this variable refrigerant flow system, it takes advantage of all those features, everything that we are talking about, like, variable expansion valve, 4-way valve systems, and variable RPM, variable frequency drive of the AC compressor, it takes all of those advanced technology and adds 3 pipes. So generally you see only 2 pipes coming from your outdoor to indoor unit, only 2. Here you add a third one, and now you have the ability for one big puppy on the outside managing few indoor. This system is not suitable for small scale system. It is medium scale system, meaning you should have at least 5-6 units. I think I can have it in my home, but like it's not something like, hey, we have only 2 bedrooms and those bedrooms have to be air cooled, AC'd. It's not really desirable for that. But if you're like, hey, we have this house and like, we have multiple ACs, yeah, it makes sense. It actually becomes economical. So you can have this sort of system. Basically few indoor unit, and you can also have multiple outdoor unit, because these outdoor units have this one paradox. How the heck you ship it? Companies would love to give you one super giant optimized heat exchanger. It's just that issue is how the heck they will ship it. It would be wrong scale. So the idea is, economics point of view, it's not from a physics point of view, this is a bad idea. From economics point of view, far more practical to A, stock the parts, B, if someone's like, hey, we need a lot of power, put multiple units, and other scenarios like, hey bro, just like, unless you really need efficiency, people will be more than well enough served with these things. So you can have multiple outdoor units. So now you have multiple indoor units, 20-30 indoor units, and you can have 5-6 outdoor units. So that allows you to scale the system at multiple ratios. Like you can scale the hell out of it, and it allows you endless possibilities in zoning, meaning now you have the actually, hey, I'm heating this puppy up, hey, I'm cooling that puppy up, meaning you can have a scenario where it's like, all the laundry clothes goes into a room that is heated up. So it's like, open the washer, it will dry up on its own. So you have a lot of option. Flexibility wise, this is butter. You do not have to worry about it. It can load balance. At optimum scenario, it can literally take heat from one place, dump it into other place. So for example, if you're cooling something, that means you are taking heat away. You can take that heat, dump it where you need it hot. This can do that. Like literally, if you have some people in the gym working very hard and they're like, hey, cool this down. And some, let's just say older couple who is like, hey, just, it's a bit too cold. You can literally take the heat from the gym and dump it into their bedroom. That can be done. So you have a lot of flexibility. You can turn it off, you can turn it on. And because these things are day one designed to be variable, they are very efficient at low loads. And like compared to normal AC, it's oscillating temperature. This is like, I'm going to maintain it and you're going to chill. Like you're going to be chill. You're just going to be fine. If you set it to 24 degrees Celsius, it stays 24 degrees Celsius. It does not go up or down. Nor compressor runs unnecessarily. It's very, what you call adaptable situations. There's like a lot of throttles, like a lot of fine tuning. So you have a lot of possibilities where you can hot and cold at the same time. Normal AC, like this sort of AC, it can either be heat or cool. It can't be like, okay, I'm going to cool that room and heat this room. It does not have that. So you can do a lot of load balancing, a lot of management. That's why people want to do. But it does come with certain penalties. Primary being you have to have 3 refrigerant lines going to every cassette unit. So generally. So this is what we are talking about, variable refrigerant system, meaning you are controlling it and you have more delicate control of each indoor unit. So how the heck this magic works? Well, it does require complex management software, meaning we could not have made this in earlier even if we tried. Like it would have required like, Apollo guidance level computer to like, okay, how the heck you are managing the temperature flow. We could have done it. Like engineering was sorted. It's just that it needs very complex lookup table. So complex management, let that be. This things runs on electronics. If you're like, hey, I do not want electronics in my system, yeah, you don't even think about it. So it needs come. And on top of that, if you're like, hey, I want something that is dead simple, never breaks, yeah, this will give you a heart attack. This has ludicrously complex valve system. That 4-way valve system that like, leaches some amount of efficiency. Yeah, look at his big daddy. This puppy eats efficiency. Again, overall system efficiency goes up. That's why people put up with this. But again, that's why I said it is designed to be a medium scaled system. Do not use it for like, oh, I have only 3-4 units. You can buy them, but it's like, not really suited for it. So you have that branch selector. So many times you will read up this sort of diagram, they will have BS written. Is generally branch selector. Do not ask me who came up with that name. They should be in English, and they should have known that BS means bullshit. But I have no idea why. So that is BS. Now what is this 3 pipelines? Well, first pipeline is high pressure gas. This gas supposed to go to condenser to dump heat. Then you have low pressure gas. This is supposed to go to compressor to become high pressure liquid, so to say. Basically high pressure gas, sorry. And then you have high pressure liquid. This you're supposed to send to evaporator so you can get cooling. So this is what you understand. The high pressure gas, supposed to go to compressor. Low pressure gas supposed to high pressure gas supposed to go to heat exchanger to dump heat. Low pressure gas has to go to basically compressor, and high pressure liquid supposed to go to evaporator. So that's why you need three of them. So people realize that having three pipelines means you have ludicrously large amount of refrigerant, like bonkers amount of refrigerant. So you could have a scenario it's like, okay, it's a building, like let's say a 10-story building, which this is optimally suited for, but you will have way too much gas. Like your tonnage won't be that stupidly high. Like let's just say it's 50 ton or 60 ton. It's not that high, but the moment they will give you the bill of the refrigerant, it would be painful, because again, you have three pipes going everywhere. It is huge, painful. So people are like, yeah, we're not gonna be using this. So a lot of engineers thought, what if we created a compromise? So compromise is this puppy. So this is advanced branch selector, which has the ability, instead of having three lines going to each cassette, it has a big branch selector. Basically, let's say you have rooftop units, floor units, this is the floor unit, and it connects to all the basically cassette, and each cassette only gets two pipeline. Now the amount of refrigerants you need goes down drastically. So because be mindful, no matter what sort of system you're dealing with, refrigerants will leak. Yeah, of course, if done very well, it should leak in 10 years. If done incorrectly, realistically speaking, you're gonna have some scenarios, and be mindful, so much is being used, it can last functioning, it will keep remaining functional for very long duration. So that's the good part. Bad part is you might be burning energy, excess energy, without noticing it. So you do realize these things does have the scenario where it's like, yeah, it eats up gas like there is no tomorrow. So this sort of system, this hyper complex system, became viable, necessary, simply because it made the system far more digestible for business owner. Where it's like, yeah, we get the cooling, we get the heating, we get the energy efficiency. It's just that every time we have to refill the gas, it's like a bank loan. Yeah, so this is the compromise. And sometimes people are like, yeah, this is also not good enough. So now you have a water system. So water is going to your fan coil units, and either the water would be hot or the water would be cold. You will have like two pipes, and refrigerant amount is now back to very little. So this is how this system works. So basically you have a blue line. A blue line you have it's after condenser. So condenser goes to the evaporator. Damn, this has so many complications. So compressor creates the basically what we call high pressure flow. High pressure flow goes into your indoor unit. Indoor unit dumps the heat. It turns into basically liquid. That liquid goes into what you call outdoor unit. Outdoor unit, it evaporates, basically takes the heat from the outside. Now it's a gas that goes into your compressor. Now generally these sort of system have multiple compressor. That also another advantage. Many times it's not desirable to run a compressor at lower RPM. Compressors are fine tuned for 1 RPM, like one sweet spot. But what if your load is changing? Hey, what if you have multiple compressor? So you can have a scenario where it's like, hey, compressor 1 goes full on, turn off, compressor 2 takes care of it. Or if it needs to, both compressor could be running at 80%. So that way they generally more time is spent per compressor being in optimum spot rather than like chugging along. So overall, yes, let that be clear. It does consume a lot of power and wastes some amount of energy in this sort of complex valve train, but it still gives you energy efficiency. So after evaporator, you run the system. This gives you heating. Cooling, super simple. You have basically compressor took in the gas, compress the hell out of it, and then it sends that high pressure gas to the condenser unit. Now the outdoor unit is behaving like condenser. Now that condenser dumped the heat, it became liquid. Liquid goes into your indoor heat exchanger. That indoor heat exchanger basically boiled it away, and tada, you get cooling. That gas goes back to the basically compressor, and that would be what we call low pressure gas. So that's the return line, the third line generally. So that's how you do it. Now here's the deal. You have to balance it. Realistically, you will barely be in this all cooling or all heating scenario. Many times when people are doing this, generally they need that odd scenario where it's like, hey, one has to be cooling, one has to be heating. So generally you will have this. This is optimum scenario where like the amount of cooling, meaning the amount of heat you are leaching from point A, it's exactly matches the amount of heat you need for other place. So you take heat from here, dump it there. In that scenario, all the refrigerants are circulating inside. They are not touching the outdoor heat exchanger. They are circulating from one to another. The compressor is still working, but it's circulating from indoor to indoor. Heat exchanger is basically you have a AC here and it's condenser here. That's all you are doing. But generally, life will never be this simple. You will have a scenario where you have a lot of cooling and some amount of heating. So at that point in time, outdoor unit works at partial pressure. So this is the working of it, like 3 pipes, sit down with it and trace it out, you will understand. It's just that high pressure liquid and low pressure gas, high pressure gas, these are just things. It's just extra pipe. It gives you flexibility. So you could have flexibility at your unit or at your branch selector. Branch selector saves you a lot of money in terms of piping, but cost money in the branch selector itself. And there are a lot of push that do not have even this much refrigerant. Be mindful, most refrigerants are harmful refrigerant, as in if they leak inside a house, person dead. If houses catches on fire and that much amount of refrigerant is there, boom. So be mindful. If people hated, like, hydrocarbon refrigerant, which are the most energy efficient, like propane, butane, those sort of things, and all the hydrofluorics, those create poisonous gases. Poisonous gases are so poisonous, it makes carbon monoxide look like a minor inconvenience. So people are like, yeah, that's still not that good enough. So idea is, now this system will have a water loop. So you have heat exchanger here, and every person, basically every cassette unit, is working on liquid. Benefit, now you no longer have that issue. So at case of fire, you have water falling on top of it. Now, how does this system compare to chiller? Because again, chiller is ancient. Chiller has been there, chiller is there, chiller will be there. So chiller is basically when you need to handle daddy size load, meaning you are starting above 100 tons. Like you're like, hey, 200 ton, 500 ton. Yeah, you're not going to even look into variable refrigerator. Those are good for flexible medium scale system. Chillers are like, bro, don't wake me up if you are below 100 tons. So at that point in time, it's not even a competition. It's like, yeah, just do that. Simply because water pipes have 2 advantages. First, they can transport energy much further than refrigerant can. Refrigerant, there is a very serious chance if you have very long refrigerant line, it might self go do the phase change. So that's an issue. Another aspect is your compressor will start to stall out. It's like, so compressor has upper limit. Water pumps, yeah, bro, it does not care. We have district cooling, as in tens of kilometers of pipe or hundreds of kilometer pipe is like, bro, that's Wednesday for district cooling or heating. All of them are using water. Water is far more effective of carrying heat or cooling from one place to another, tens of kilometers. And again, if it leaks, not that big of an issue. Building catches on fire, not that big of an issue. So it's water has the ability to transport a lot of energy very far. That's the good part. Second, it's safe compared to refrigerants. So that is there. And long refrigerant line is something that you cannot just like ignore. And chillers also have this advantage that you can use those sort of flammable system. Why? Because they are generally put in mechanical room. Meaning, if an engineer did his job right and they are assuming this is a mechanical room, they will design it to go boom. As in, like kitchen. Like if you have kitchen and you have propane and butane, kitchens are designed to handle fire hazards. This will be designed in such way. It's like, hey, we have propane or ammonia. Ammonia is the best. The best refrigerant is ammonia. But again, it's toxic. But if it's concentrated in one place, you can have a safeguards there. Like, hey, design this place to have a positive airflow. Design this place to have a fire, resistance, so to say. So it can be done. So that itself gives you far more choice when it comes to your refrigerant. Second, everything is closed loop. As in, you have condenser here, evaporator here, compressor there, a valve there, the end, go home. Everything is tight. So all the phase change is happening in tight loops. So you get a lot of basically a lot of very effective coefficient of performance. That's the good part. And you can achieve what we call that heating and cooling in this also. It's just extra plumbing. You just have extra plumbing, but it's not impossible. It's hassle. It's not impossible, it's just hassle. It can be done. It has been done in many scenarios and has been done from decades ago. It's just that it's hassle. It's like, so that is there. So there is a lot of push for what we call hybrid VRF. That's what I'm talking about. Like people are like, hey, I do not like the idea of having so much refrigerant that anytime you have to do servicing after 10 years. It's like, yeah, please open a bank loan. So use water. And water is the better conductor anyways, just use water. But again, it does require this branch selector to have almost its own water loop system where it's like, hey, I have a hot water loop, I have cool water loop. It is tedious, but it can be done. So if I'm not mistaken, Mitsubishi is working hard on it, on hybrid variable refrigerant flow. So the idea is you're going to have outdoor unit and each branch selector can handle 8 to 16 units independently. But whenever you really need some big load, just buy a chiller. Like in terms of raw COP efficiency, there is no discussion. Yes, you will have to spend some effort into making basically heating and cooling loop every fan coil unit. It will be messy, but it is doable. And again, water pipes are far more comfortable for people in a hazard scenario than refrigerants. So chiller has still its place. It's chilling. Okay, don't worry about it. It's like a lot of people talk, oh, chiller will be replaced. Yeah, no. Medium load, I can easily see that, but large load, no. So this was my presentation on basically variable refrigerant flow systems. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst a friend. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me assessment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.